Welcome to the 7th lab in Physics 187. In this week's lab and next week's lab, we'll begin to look at techniques for measuring the masses of the stars. And we know that in order to find the mass of an object, we need to be able to measure the gravitational effect of that object on another object. In the case of binary stars, what we consider is the gravitational effect of those two masses on each other. The technique that we'll be using this week will be for stars where we can actually see that there are two stars in that binary system. So using a telescope, we can resolve those two stars, and this would be a category of binary stars that we call visual binaries, because we can actually see the two distinct stars in that system. What that will allow us to do is measure the angular separation of those two stars, and from that angular separation and the distance to those stars, we'll be able to actually find a value for the size of the orbits of these two stars. Then, because we can measure the speed of those stars using the Doppler effect, like we did last week when we measured the actual motion of stars, we'll be able to get a value for the speed of those stars in orbit around each other. And then using Newton's law of gravity and some additional physics techniques, we can actually come up with the value for the mass of the two stars in those binary systems in terms of the parameters we can measure, their speed and their separation. And so the equation that we would use to find the mass of star 1 would be a combination of the sum of their speeds multiplied by the speed of the other star multiplied by the separation or the size of their orbit divided by Newton's gravitational constant. Again, the value for Newton's gravitational constant is in your lab manual at 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The relationship we'll be using to find the speed of the stars is the same relationship we used last week. We'll look at the fractional change in wavelength. We'll multiply that by the speed of light, and that will give us the speed of the stars. Notice you'll need to do this for each of the two stars in the binary system. And finally, when we look at the stars through our telescope, we'll be able to get an angular separation between those stars, and we'll use that angular separation and the known distance to get the size of the orbit. The relationship between the distance to the stars, their angular separation in arc seconds, and this conversion factor that converts from arc seconds to radians is this equation right here. So the distance multiplied by the angle in arc seconds divided by this conversion factor will give us the size of the orbit. Let's go ahead and take a look at virtual astronomy to see what this lab actually looks like. This will be visual binary stars. When you open up the lab, you will get a view of these two stars orbiting in the sky. And so what we're actually seeing is we're seeing a face-on view of these orbits. If you want to, you can change the viewing angle so that you're looking at the orbit edge on, and you can see the stars moving back and forth across the view of the sky. Whichever orbit you use is fine. Use whichever view you think is easiest for you to get the information. You'll want to make sure that you turn on a grid. And what you will use this grid for is you will use the grid to find the angular separation of the stars. The resolution of this grid is given to you in your lab manual. Each square on the grid corresponds to a width of 1 arc second. I'm going to slow down the animation for just a little bit and stop it right now where I think the two stars have reached their maximum separation. I'm then going to use this information to find the approximate angular width of the orbit. So what I need to do is I need to measure the center-to-center distance for these two stars. Starting here, I'm a little bit ahead of this line, so 1, 2, 3, 4. Here's about the center. It looks like the angular separation of these two stars is about 5 arc seconds. Make sure you note that. You won't actually use that value in the calculation until you get to the point where you're ready to check your answers. To find the speed of the stars, right, what we'll do is we'll just simply click on one of the stars. And when you click on that star, notice the spectral lines for that star will come up. And you'll do the same thing you did last week, is you'll click on the individual spectral line and you will see the reference line right here, which is what the light from that star would look like if the star was not moving. And then this line is Doppler shift, 1, 2, a little bit more than 2, about 2.1 squares to the right. Notice the scale has changed. Now each of the squares is worth 0.005 nanometers. For this particular lab, we'll only look at 2 spectral lines. We'll assume that you've gotten better in measuring Doppler shifts, and you'll use this violet and you'll use this green line to measure the lines. If I click on the other star, I will get a similar spectrum. Notice the one difference in this case. In this case, the lines are actually shifted in the opposite direction. And you'd expect that when you think about what's happening to these stars, is one of them has to be moving toward you and one of them is moving away from you. So you'd expect one of the star's lines to be blue shifted if it's coming toward you, and one of the star's lines to be red shifted if it's moving away from you. In this lab, you'll also have a spreadsheet to help you with those calculations. I'll just pull that up for a second and show you what it looks like. So for star 1, oh sorry, I guess you do have to do also all the spectral lines. It's only 2 stars, so it won't take you very much time. For star 1, you'll measure the violet, 1, 2, 3, and you'll do the same thing we did for last week's stars. You'll find the average angular or average fractional wavelength shift and then use that to find the speed. You'll do the same thing for star 2, and that will give you these values to put in this equation. The last quantity you need to find is the radius of the orbit, and you'll be able to find that with the last step in virtual astronomy when you go to check your answers. Notice when you look at the check your answers box, they will tell you that the stars are about 10 light years away, or a distance of about 9.58 times 10 to the 13th kilometers. This will go into this particular equation right here. The one caution I will make for you is that this equation here and here, they both expect the radius to be in meters, not kilometers. So you'll need to make sure you convert this distance to meters by multiplying by 1,000 before you put it in this equation to calculate this separation. Notice they're also asking you to convert that distance to astronomical units. What this is really doing is giving you a sense of how the size of this binary system compares to the size of our solar system, right? If you were to get a distance of 0.05 astronomical units, that would be a very, very closely connected binary pair. If you get something comparable to 5 or 6 astronomical units, that would be similar to the separation between the Sun and Jupiter. So this value just gives you a sense of the scale of the solar system. And then one more caution. The mass that we will calculate from these equations over here will be in kilograms. Notice very carefully what they're looking for here is they're asking for the mass in solar masses. So the conversion factor between kilograms and solar masses is in your lab manual. It's 2 times 10 to the 30th. The answers that should go in here should be typically somewhere between about 1 and 10 will be the typical masses that you'll find for these binary mass systems. Don't be afraid to draw some conclusions when you write up your report. You know, I would hope that you would look at and compare when you have a massive star and a light star in a system, how do their speeds compare? Do the massive stars move quicker or slower than the lighter stars? Things like that would be appropriate observations to put into your conclusion. If you have any questions, please send me an email. Good luck with this lab.